Small changes, big effects, miscalculations and collapsing bridges. You may be wondering where I'm going with all this and how these are all connected, but in about 12 or so minutes we'll be on the same page. I'm going to link all of these things through one word: engineering. For those of you who don't know, engineering is the union between mathematics and science, applied in order to solve real problems. It is broad and can be found in every walk of life, but today in particular I'll be talking about civil engineering, which is concerned with structures and buildings. Engineering itself is analytical, logical, and vital to maintain and help society grow. As humans, we are chemically wired to make mistakes. It is natural and written into our DNA. How we adapt, learn, and develop ourselves from these mistakes is a unique factor differentiating humankind. For some situations, we simply do not have the knowledge to understand whether a decision will become a mistake, thus, sometimes an event becoming inevitable. Small mistakes have the potential to cause significant impacts. Let's think. Something as simple as buying a one-use plastic, like straws, leads to the catastrophic end of humanity as we know it. Dramatic, I know. Thinking more about engineering, consider the Hubble Space Telescope. Created giant leaps in terms of astrophysics, and the engineering behind the project was incredible and challenging even for experts in the field. However, there were setbacks and potential failures throughout the journey. One key moment was the miscalculations that led to blurry photographs. It was discovered that the telescope's main mirror was too flat. Although a microscopic error, the imaging was too blurry, and the future of the project was threatened. It was theorised that a device used to test the mirror had a tiny fleck of paint on it, which distorted the measurements. To put this into perspective, a telescope 13.3 metres long, the size of a school bus, malfunctioned due to a speck of paint with a diameter of 1 millimetre, the thickness of your average credit card. It's fascinating to see something so small have the potential to cause such detrimental consequences. As humans, we learn from our mistakes as they help us grow. Being conscious of past mistakes is essential to make sure we don't make them twice. As science has incredibly progressed over the last 100 years, we are more aware of phenomena to explain different occurrences in nature. Let's take a slight detour here, and I'm going to give some background to something that I personally find fascinating: suspension bridges. Suspension bridges are bridges that have main towers and steel cables supporting a roadway which extends across large expanses of water. Some examples you may be familiar with are the Golden Gate Bridge, Brooklyn Bridge, and the Millennium Bridge, which I will be coming back to. One bridge you may or may not have heard of is the Tacoma Narrows Bridge, which is a case still so famous that it intrigues mathematicians, physicists, and engineers to this day. It spanned between Tacoma Narrows in Washington to the Kitsap Peninsula. First opened in July 1940, after 2 years of construction, it was obvious from the beginning that there was lots of movement in the bridge in the windy conditions, which proved it to be very unstable. And this continued even when open to the public. Engineers reinforced this bridge with several damping measures, however it had no effect. After several months, the bridge collapsed in 40-mile-an-hour winds, but the motion of the bridge this day was distinctly different to the usual vertical movement, as this time it had rotational and oscillatory nature to its motion. These oscillations grew in amplitude until the force exerted on the bridge was enough for it to collapse. This occurrence is widely studied and used as examples in physics, maths, and engineering as a key example of force mechanical resonance, but could also be presented and studied under the light of aeroelastic flutters. Obviously, to understand the nature of this failure, we need to learn more about the motion itself and how different factors would have affected the likelihood of the event occurring. Firstly, let's consider the motion of the bridge. As I mentioned earlier, initially the bridge moved vertically in windy conditions, which was due to the flexible nature of the structure. However, a fundamental point in this event was the change in motion on the day of the collapse, from regular vertical oscillations, which were normally observed, to a twisting, alternating oscillation of the bridge itself, which had never been observed before. This initial vertical oscillations were A, due to the flexibility of the design, but more interestingly, B, the idea and concept of mechanical resonance. Thinking about the design, its main priority was being cost effective, and seeing as this particular design was the cheapest, the board decided to choose it. Key factors that reduced its costs was the design of the stiffeners, to make sure that the elastic distribution of the bridge's suspension cables was able to absorb the wind pressure that it could encounter. So, plate girders on the right were used instead of trusses on the left. This made the design much less bulky and more favourable in terms of cost. So initially, all seemed to go well. However, this decision was unfortunately not well thought out and did not consider all circumstances. The bridge proved to not be rigid enough and was flexible enough for the centre span to rise and fall with several amplitudes of feet. Mechanical resonance is an occurrence studied in physics and engineering, which is the tendency of a mechanical system to produce oscillations of high amplitude when the frequency of the oscillations matches the natural frequency of the system. This is a lot of words and probably quite confusing, so I will try to explain the best I can now. Resonance is a condition or state that a structure can be in due to its sensitivity to certain vibration frequencies. Depending on many factors like shape and size of the structure, the frequency at which vibrations will affect a structure vary. Natural frequency is the frequency that a structure in equilibrium vibrates at, where equilibrium means there are no external forces acting on the system. When the natural frequency of a system is near to or the same as the frequency of the force applied to the system, resonance occurs. To think about an easy example of resonance, we can consider a trampoline. When two people jump at the same time, the same exact time, they both go doubly high in the air, this is resonance in action. So, considering our bridge's oscillation to be sinusoidal, which means they follow a sine or cosine curve, we can see that the amplitude will increase in response to the resonance. So, this initially provided major disruptions and gave the bridge its famous nickname, Galloping Gertie. Now, the fateful day of the collapse, November 7th, 1940, there were 40-mile-an-hour winds, and the usual vertical oscillations dramatically changed form to horizontal torsional oscillations where the bridge eventually broke down. After long investigations, the collapse was deemed to be by two potential failure causes. One, aerodynamic instability due to the natural frequencies in the system, and two, the periodic nature associated with eddy formations. Aerodynamic instabilities were caused by the change in the design of the girders, which involved the implementation of the plate girders, which were notably the first of that type. These were an attempt to support the roadway itself. Comparatively, a normal truss, which is a series of metal triangles you would usually see on the side of a bridge's deck, would allow wind to flow through it, which causes less instabilities. However, this was a solid truss with no gaps in its design, so the wind flow was directed to bend around the trusses. This proved to be very unsafe and caused the instabilities to become a hazard, even when mild wind would cause unwanted motion in the bridge. When assessing this motion to see if it had the possibility to cause harm and potentially collapse the bridge, the motion itself was said to be transverse, where one side would rise and the other would fall, following again some sort of sinusoidal curve. However, due to the heavy mass, thus the heavy weight of the bridge, the decision was to not change the bridge, and the weight was thought to be enough force to be able to counteract these winds. But, as we discussed briefly earlier, the day of the collapse, the motion dramatically changed from translational to a torsional vibration mode, which involved the left-hand side rising while the right-hand side fell, which is more of a twisting action rather than the earlier undulating pattern. This vibration was caused by a phenomenon called aerostatic fluttering. Aerostatic fluttering can be described as an instability in a structure due to an interaction between aerodynamic, inertial, and elastic forces. This unstable structural oscillation has a definite frequency and flow-induced motion. Energy is absorbed from one airflow in one mode to increase the amplitude of another. A mode of an oscillating system is a stationary wave, and energy will be absorbed from one mode to another until critical flutter speed has been reached. Critical flutter speed is the maximum energy a mode can absorb to increase its displacement and amplitude, hence its bending and torsion flexure, until the structure will fail. The vital part that could not counteract these increasing forces from this fluttering was the suspender cables. These cables could not withstand the increasing force, and these broke in turn. Almost all of the midmost of the deck fell into the water below. The second potential cause of this failure of the bridge was the periodic nature associated with a different form of oscillations. This cause considers both aerodynamics and resonance, which makes it to be a more probable candidate than the first idea, which only considered aerodynamics. This particular phenomenon is called vortex-induced vibrations, which can be abbreviated to VIV. They occur when fluid flows, like wind or water waves, pass a solid body, which leads to a concept called the Kármán vortex streak. It is a repeating pattern of swirling vortexes caused by vortex shredding, which is responsible for the steady separation of a flow of fluid around blunt bodies. The Kármán vortex streak only forms at discrete sets of flow velocities, which are specified by Reynolds numbers. Although very, very complex, if you are interested, it can be mathematically modelled through a number of techniques, either using full Navier-Stokes equations with K epsilon, SST, K omega and Reynolds stress, and large eddy simulation turbulence models, or by solving numerically with dynamic equations like Ginsburg-Landau equation, which is on the board, part of it. The constant repeated wake vortices generate periodic fluid forces on the body, causing it to vibrate as long as the vortices are shed at a frequency near to or equal to the natural frequency of the system. This sensation itself is referred to as lock-in, and the resulting effect is a large amplitude of vortex-induced vibrations. Overall, this high-frequency vibrations leads to high-frequency cyclic stresses and therefore high rates of fatigue damage to the structure, and in this case, the bridge and its supporting trusses are affected. Although it may seem like we have learned from our past mistakes and mitigated the effects of mechanical resonance and vortex-induced vibrations within suspension bridges, similar issues of lateral oscillations and swaying was experienced more recently and closer to home with the Millennium Bridge. The Millennium Bridge, within a few days of opening, had experienced lateral swaying movements due to the resonance from pedestrians. With over 2,000 people crossing the bridge every day, the frequency of the footsteps resonating with the reinforcement of the continual stress from the force of the amplitude of the oscillations in the bridge increased. But only a few months after opening, the bridge was closed to reinforce it with damping methods to mitigate the effect, and the bridge now experiences little to no oscillatory motion. Before I leave the stage, let me leave you with this. The ramifications of minor human errors can have significant impacts. Again, something as small as an inconsideration of airflow can cause a bridge to collapse. As society progresses, we are acquiring, developing, and understanding more about the way the world works every day, and I wholeheartedly believe that making mistakes is a vital part of human nature and allows us to become a better community and make substantial scientific advancements. Lastly, I want to say a major thank you that you've taken the time today to come and listen to me. It has given a huge amount of pleasure for me to be able to share the joys and passion that I have for this subject, and hope to be able to leave you with some food for thought and perhaps a different perspective on the world.